of this session on critical challenges in modeling past and future evolution of the Antarctic and Greenland ice sheets, scales, uncertainty processes, implications for sea level. And I thank all the speakers and all the other attendants in the name of all my co-hosts. These are Rupert Gladstone, who is present here, and also Felicity McCormack and Chen Zhao, but both of them are on different time zones, and they were keen in chairing the first session, which was at a very unusual hour for Europeans. So we made oceanic version, and we have a European version of this session. A bit of housekeeping that I have to say. So all the questions can be asked in the chat box, which is a function that you find at the bottom of your Zoom channel. All these sessions are recorded, and they will be made available to registered participants. They will be also uploaded to the SCAR YouTube channel. However, if you don't want your presentation to be made available on YouTube for one reason or another, you should contact SCAR 2022 at elbonmeetings.com before the 12th of August in order to opt out. And then finally, I would like also to point you to the e-poster, the e-posters that can be visited and that are available throughout the whole Open Science Conference. And it's in the e-poster exhibition space on the events platform. You can just browse there and you go to the name of this session, which is probably the longest name that you find in there. So that is easy to find out. So without, so all speakers have a slot of 15 minutes, and that is 12 minutes for the talk, and then we have 3 minutes for questions. And these questions, as I said, can be put in the Q&A or the chat that is normally accessible to everyone. And so without any further ado, and I hope I didn't forget anything, Rupert, then we start with the first presentation that is going to be given by Antonio Martinez on the Antarctic ice-ocean interaction with the ice sheet model YELMO. So Antonio, if you can share your screen.
Yes. Just the one thing to mention, I'm going to raise my hand after 10 minutes. So for each speaker, if you see me raise my hand like this, hopefully that's fairly visible. That means you have 2 minutes left, and then Frank will start to get rude after.
Yeah, so I'm the good cop and Rupert is the bad cop to keep time here.
Okay. Can you see my screen?
We can see your screen, but not in presenters mode yet.
Now?
Yes, perfect. Thank you very much.
Okay, so I shall start.
Yeah.
So good afternoon. My name is Antonio Juarez, and I am a PhD student at the Faculty of Physics of the Complutense University of Madrid in Spain. My work for this presentation is based on the master thesis that I did last course, and it focuses on the interactions between ice and ocean in Antarctica and how they will influence the future sea level rise and the dynamic ice loss in a changing climate. So during the presentation, I will try to explore the future evolution of Antarctica with the ice sheet model YELMO, developed in our group in Madrid, and that you can find on this GitHub repository. And I will emphasize the great uncertainty derived from physical processes such as basalt melting. And in order to do that, we have proceeded considering 2 periods, one until 2100, looking for a comparison with the results from Cerusi et al. For the ice sheet model intercomparison project, ISMASS, and another an extension towards the year 2500 to look further into the future. Also, there are other processes producing uncertainty in the assessment of Antarctica, like, for example, subglacial hydrology, which could affect ice sheet dynamics, and in which we are also interested in our group for its implementation in our model GELMO as future work. So as we know, bedrock elevation in Antarctica is unevenly distributed on the continent. On the east, most regions are above sea level, but the west is below that level. So the ice sheet on the west, the waste, is marine-based, and therefore profoundly influenced by the heating of the surrounding waters that has been observed in the last decades. So this could have drastic consequences in terms of sea level, especially when the ice sheet is grounded over a retrograde slope, as you can see in this image, and producing what is known as the marine ice sheet instability or mist. So sea level rise in the future is a fact that we can ignore if we have some of these processes into account. And the first result of the ISMASS project by Felicity et al. Remind us how it could be at the end of this century. Nevertheless, there is an important uncertainty in those results that we can see on this figure on the right. So our plan was to recycle some of the experiments of this study by Felicity to see the contribution of GELMO. In order to do that, we have used the quadratic non-local basal melt parametrization of Jourdan et al. That translate thermal forcing, anomalies in temperature or thermal forcing represented by the symbol TF here, in basal melting. And it uses the different sectors in which Antarctica is divided that you can find on this figure on the right one. Regarding the experiment that we use to do this parametrization, we use as forcings the anomalies of the Norwegian model NORS 1M in the context of a RCP 8.5 scenario. And in turn, we use two calibration for the parameter gamma 0 on the formula, which is the rate exchange velocity. One of these calibration is mean ant, based on mean Antarctic observation, and the other is pi-IGL, based on observation over the Pine Island Glacier, which is the region of Antarctica with the highest melting rate. So we have a control experiment, 3 experiments using mean ant, and 1 experiment using pi-IGL, all of them varying the value of the parameter gamma 0 on the formula. Results until 2100 show a decrease in sea level for the 3 experiments using mean of around 10 millimeters, and an increase for the experiment using the pi-IGL calibration of around 20 millimeters at the end of the century. So we obtained some uncertainty in our result, but nevertheless, they are on the range of the result of accuracy that I have shown you on the motivation of this presentation. Separating the contribution by regions, the Antarctic Peninsula, the east and the west, we can clearly identify the West Antarctic ice sheet as the main contributor to sea level rise, and the East Antarctic ice sheet acting with a counterbalance effect, gaining in accumulation. Extending the simulation until 2500, we can see that the decrease observed in this century is inverted and an exponential growth begins to happen for all the experiments, which is especially remarkable for pi-IGL, that in this case could surpass more than 80 centimeters at the end of that century. And again, the West Antarctic ice sheet is going to be the main source for this contribution. I have to say that to do this extension, we had used the average anomalies in the forcing of the climate model between 2090 and 2100 for the rest of the 400 centuries, remaining until 2500. So what is obtained here is an infra-estimation. Regarding the anomalies in 2D for the pi-IGL calibration with respect to 2015, we can see first for ice thickness on the left that ice loss will be concentrated on the west part. Here is represented by red colors. And we can also observe that there is a migration of the grounding line towards the interior. And we obtain also a collapse of in the Ross ice shelf. For surface velocity, we can see an acceleration in the surroundings of the grounding lines along the continent, which is due to the debruticing effect that Antarctica will experience as it loses its ice as time passes. Just to finish my presentation, I would like to remark that apart from basalt melting, there are other processes involved in uncertainty in Antarctica. And one of them in which we are particularly interested is subglacial hydrology. There are many evidences that under the ice sheet of Antarctica, the landscape could be something similar to what is shown on this figure, with rivers, lakes, and channels running through the continent that could potentially affect the dynamics and sliding of the ice, which is above the water. But for the moment, in Gelmo, there is only a local method implemented with no advection, but we are planning to now to introduce a novel method considering advection as a project for my PhD in order to answer the question that Weirman asked in 1962, which is how water layer at the base could impact sliding. So as conclusion, I would like to say that there is a strong dependency in the calibration of basalt melting, which lead to some uncertainty in our results. But nevertheless, they are in the range of the result achieved by CERUC for the ISMASS project in 2020. In 2100, sea level could be between minus 12.5 and 90 millimeters. And in 2500, it could surpass 80 centimeters. We have also identified the West Antarctic ice sheet as the main contributor, and the is acting with a counterbalance effect. As future work, we are also planning to do new simulations for this in this kind of ISMASS test with forcings until 2300 with other climate model and using a higher resolution, because I forgot to say that in this result that I have shown you, we have used 32 kilometers as resolution, but now we are planning to use 16. I will finish saying that now we are interested in subglacial hydrology in our model GELMO to assess the effects over the Antarctic continent. And this is all. Thank you for your attention.
Thank you very much, Antonio. Are there any questions from the audience?
There's one in the Q&A already.
Oh, okay. All right, in the Q&A, it's Gilles who asks, which PCO2 was used in the period 2100 to 2500?
Sorry, can you repeat the question?
Which CO2 concentration was used for the period 2100 2500? So for the RCP 8.5 after 2100.
I think that I don't know that answer, but because we have used the forcing from the climate model, but I don't know exactly what.
I think that no reason there are simulations that go until 2300, but what do you do then after 2300? Do you keep the atmosphere forcing, the ocean forcing constant?
For the extension towards 2500?
Yes.
Okay. We have used the mean values in the anomalies between 2019 and 2100. I mean, the last 10 years of the period in which we have the data. So, and we have proceeded with that data for the rest of the centuries. So, as I have said, it's an infraestimation what is obtained. But now we are planning to repeat all the computation with the data until 2300 and see what's happening. Maybe for next conference, I will have some results.
Yeah, I have two questions. Thank you very much for that response. First of all, what initialization was used here with YELMO? What method was used? We have an spin-up of 30,000 30,000 years until 1900, and from 1900 until 2015, we had used the same proceeding in that Jordan and Serusi used on their paper, using some. I can't remember because I did this for my master thesis, but there is a period between 1950 and 1994, and there is another period from 1994 to 2015. But I can't remember exactly what we have done, because I needed a lot of help as I was a master student. By yeah, it's already impressive the work you did for a master thesis.
I received many help from Alex and Jorge and Marisa. And so what explains, if you look at the sea level contributions, you have a very slight negative sea level contribution, or slightly up, but then suddenly after 2070 there is a drop in sea level. Well, you get a strong negative sea level contribution. So what explains that? What happens after 2070 that explains that suddenly you get more mass gain? It's in those. I think that this can be explained by the sensitivity of all the rest of the parameters that we have used in the name list to launch the simulation. That maybe they are at very low values, and maybe they can influence that, because if we extend the simulation, we can see that at a certain point it starts to increase, which is what is expected under our RCP 8.5 scenario, I think. So I think that is due to the sensitivity of the rest of the parameters that can influence in these calibrations. Okay. I don't know if that's the answer. No. It's perfect as an answer. Thank you very much. Well, great work. And I don't know whether there are any other questions from the audience. Rupert, you check this a bit.
That's the only one in the Q&A. I don't see any in the chat, so I think we can move on if we have a speaker to move on to.
Yeah, is Luciana Lima there?
So Luciana is not currently in the panelists group. Luciana, if you are an attendee, if you're the one with the name Lu Li, you need to accept the invitation to promote to panelist, or it could be that she's just not there.
Yeah, it could be.
In which case we could move on to.
Well,
Kenny.
in this case, no, I think that in that case we should have a little break to keep to the time, to respect the schedule.
Okay, there's a message from Mike. Believe Luciana couldn't make it today, but thought she had recorded talk. I think the IT people are present and they would let us know if there was a recorded talk. Thanks for letting us know that, Mike. So sorry, Lee, if I've been hassling you and you're not actually the same person at all.
So maybe there is a recorded talk. Is there a recorded talk for Lucian Lima IT team? No answer from the IT team. Yeah, there are two options. Either we wait a bit until we get to the time, or we slack things a bit, give more slack to people and start earlier with Kenny. I don't know what is preferable. I check with the panel. What does the panel think? Otherwise, I don't mind if we start already with Kenny, unless he was maybe waiting for some particular people in the audience that were waiting until 13:45 UTC.
No, I can speak a little bit slowly.
Okay.
Well, in that case, too bad that we don't have this fantastic talk on freshwater contributions on coastal dynamics on peninsula, but then we will continue with our third presentation by Kenny Matsuoka from the Norwegian Polar Institute and on the RINGS initiative on the Antarctic ice sheet. So Kenny, if you can
Yes.
share your screen.
Yeah. Yeah. Right. Can you mind?
Yes, we see this.
Okay. Well, thank you so much. And hello, everyone. I would like to talk about the RINGS initiative that we are running 1.5 years now. Here I put the 8 steering committee members: Chui, Fausto, Lene, Tom, myself, Geir, Felicity, and Kirsty. I would like to give, I hope, a good overview and some update from the workshop in late June. Okay, I think you already heard a lot about the RINGS already, but just in case, I would like to mention it very briefly. The RINGS initiative or RINGS action group target to measure better topography in the coastal regions of all around Antarctica. And our primary interest is the better topography at the grounding line, because that is critical knowledge to measure ice flux, of course, present day ice discharge flux from the ice sheet. So in other words, this is a main component of the Antarctic contribution to the global sea level rise. We are also interested in the bed topography under the ice shelf or the ocean there, because these bathymetry define the ocean floor under the ice shelf and the interactions between ice shelf and ocean. So this is the main driver of the future change of the ice sheet. So bathymetry or bed topography there is important as well. And also, the bed topography slightly inland of the grounding line is important to spur ice shelves, ice sheet response and the grounding line in the future. So we wanted to make the airborne geophysical measurement at the grounding line and slightly seaward and landward all around Antarctica. So that's why we call this project as RINGS. And this is plural, not a single A ring. It's a RINGS because we want to make landward rings, primary rings, and the seaward rings all around Antarctica. Or maybe you ask to me that, well, Kenny, bed topography has been measured for the last many decades, and it's not really necessary. Well, I think it's quite wrong, actually. The left figure shows the data, radar data used for the BedMap tool, say 10 years ago. And the right one is showing the radar data used for the bed machine compilation very recently. So you can see the very great improvement of the radar data coverage of the bed topography in the last 10 years. So, well, overall, Antarctic radar data is getting improved very rapidly. However, if we see the grounding line very closely, data is not rich enough. So here we analyzed the radar data used for bed machine and to see how closely radar data is actually present near the grounding line. So we checked this issue all around Antarctica. That is a 62,000 kilometer long at the end. And we found that only 6% of the Antarctic ice sheet, Antarctic grounding line has radar data, at least one radar data within half kilometer, and another 6% has radar data within 1 kilometer. So this, say, 12% of the Antarctic grounding line has probably very good data. However, more than 50% of the grounding line has no data within 6 kilometers, and the 28% of the grounding line has no data at all within 20 kilometers. So to estimate the ice discharge flux as of today using the satellite data or the ice flow velocity, the eye thickness there is really critical knowledge, but the 28% of the grounding line has no measurement within 20 kilometers. So that's why we really need to measure the topography in the coastal regions. Well, maybe you ask me that, well, some regions, say Amundsen Bay, has a lot of surveys recently. So some region may not need to make any more measurement. Well, my answer is no. The right diagram showing the data availability of 8 regions around Antarctica. In each pie chart shows data availability. For example, Amundsen Bay region has radar data most rich way. So about 31% of the grounding line has a data within 1 kilometer, but still about a quarter of the grounding line has no data within 5 kilometers. And that is the best case. You can see other regions such as Enderby-Land or Dronning-Maudland has no data within 5 kilometers for, say, quarter of the grounding line in these regions. So we concluded that there is no region that has enough data already, and we really need to make systematic better topography measurement all around Antarctica. Well, still some people say that, Kenny, there is a better machine, we can calculate. Yes, true, we can calculate, but model is a model. Model cannot be the data. The model need the data. That's why we really need a measurement. And better machine is a great tool. I really think that is a game changer. But currently, better machine works only 10% of the Antarctic ice sheet because the flow speed is not high enough to best constrain the mass conservation. So you can see that where the mass conservation method is worked for the grounding line and the way it doesn't work. And the right figure showing the uncertainty, bed elevation uncertainty histogram. You can see that when the mass conservation method is working, then bed elevation uncertainty is relatively good, 100 meter or 200 meter or less. But if there is no, the ice flow is very slow and the mass conservation doesn't work, and bed elevation error is not calculated, it is assigned like a 20 meter per kilometer from the data point. So you can see that we do not really know the uncertainty of the bed elevation in these regions. So I hope that I made a case why we need to make more airborne geophysical surveys all around Antarctica to measure bed topography and ice thickness. So we started the action group 1.5 years ago, and we plan to have the workshop in May this year, but it was delayed to June because of Corona. And finally, very end of June, we managed to have the hybrid workshop in Tromsø. We have about 60 participants and nearly 100 online registration for this workshop. And thanks to the very generous support from SCAR INSTANT, Research Council of Norway, Technical University of Denmark, British Antarctic Survey, we attracted many early career researchers to this workshop. And even for the online participant, more than half of the registration came from the early career scientists. So we're very happy to attract and generate the interest in the early career generations, and they made very significant contributions. I announced earlier that we make the all talk videos ready before the SCAR Open Science Conference, but sorry, we have some technical issues. So it's almost done. So all talk videos would be available at the SCAR's YouTube channel soon after Open Science Conference. And we are working to prepare the manuscript to summarize outcome of this workshop. So I would like to briefly summarize outcome of this workshop. What we did is first we identified first high priority science questions, each for primary ring, landward ring, and seaward ring, and what measurement is needed, and what kind of ground-based measurement is necessary to supplement airborne geophysics. And here I summarize the science questions, first priority, second priority, and third priority for the primary ring. So the first priority question is what's the ice discharge and its rate of change in the future? That is the main goal of the rings anyway. And the second priority question is how does bed structure affect grounding zone dynamics and migration? So we say grounding line, but it can move and it is uncertain to identify. And the third scientific question is what is the subglacial discharge from the ice sheet? That's a subglacial meltwater, and how does it affect the vessel melting in the grounding zone, slightly seaward of the grounding line? So we agreed that we need to measure ice thickness and the bed topography along the current grounding line, and also we need to measure surface mass balance. That is because we cannot put the airborne geophysical survey lines exactly at the grounding line. Here you can see the diagram, the blue, the bottom part is ocean, and the grounding line has a very complicated topography, and we cannot make many turns of the airplane to exactly follow this grounding line. So we need to go somehow simplified flight lines. Then we need to calculate the flux at the flux gate slightly inland and account for the surface mass balance to calculate the real ice discharge flux at the grounding line. That's why we need to measure surface mass balance. We can do microwave radar surveys from the airplane, but still we need a foreign cause to date stratigraphy detected by radar. So we need both airborne and ground-based surveys. For the landward ring, the first priority science question is what's a control and influence of a vessel friction and its potential change in the future. And the second priority question is what's the surface mass balance feeding ice flow to the grounding line, the same as the primary ring question. And the third priority is how has the ice sheet changed in the long term? So to address these questions, we identify that ice thickness and bed topography is of course necessary, and how inland we need to go, that's the question, and it's not a conclusion, but at the workshop we tentatively somehow agreed that we need to consider the grounding line position modeled to retreat by 2300. And also surface mass balance need to be measured to the inland, and its inland limit is probably less than 15,000 meters above sea level, or some locations where surface mass balance would be small enough so that uncertainty can be acceptable to calculate mass flux. Again, foreign core is necessary to date the foreign stratigraphy and calculate surface mass balance. For the seaward ring, the first priority question would be what's oceanic melt and freeze? And the second, how does ocean heat travel to the ice sheet base and the grounding line? And how does ice damage, say, rift or crevasses influence stability? So again, the bathymetry under the ice shelf or bed topography is critical measurement. And at least we want to have 1 point for every single ice shelf, but of course it is too little. But ideally, we would like to make a grid survey of the 5 kilometer spacing. And not only under the ice shelf, we would like to know the bathymetry over the continental shelf. And then during the workshop, we identified that, well, if we send the airplane to the cabin front, we can also drop oceanic probes from the airplane to measure temperature and salinity of seawater at the ice front. Airborne survey is very powerful, but it's not comprehensive. So we need APS measurement for the ice shelf thickness change and the radar profiles from the inland to the offshore and multi-boom bathymetry to constrain the gravity inversion. And the shipborne CTD is necessary to supplement the airborne ocean probes. So in this way, we identified airborne geophysics is very powerful, of course, but we need a lot of ground survey or the shipborne surveys. So this is really multidisciplinary effort to make a comprehensive knowledge in the coastal regions of the Antarctic ice sheet. We found the common challenges to implement survey plans in the individual regions around Antarctica. No one can make all measurement alone, so we need to combine many projects together. For that purpose, we need to compile the information about the logistics support and its time window. We did some initial work, as you can see here. We show the runway and flight range of the twin water in this case. And of course, we need for ground-based work. And then also there is already ongoing project planning the field work coming season, for example, and we need to implement RINGS protocols to these funded project so that we can start to get the data as soon as possible. And this is a huge, at the end, very huge compilation of the data. So we need to follow fair data policy with a well-documented metadata, so that the people can possibly reproduce a high-level product. And then this would be a combination of the many data sets. So it's really useful if we can have the standard data stream for all surveys. And the computer models can help us to survey planning, and also they can benefit from us as well. Satellite community is also a very close collaborators for this airborne geophysics project. We recently wrote the EOS article and the white paper. I will share the DOI later, so please check them if you have interest. Okay, so the RINGS action group is going to extend 4 more years, and then the membership is open. And the membership is individual, so even if you find your institutional logo here, that means your colleagues are signed up, but you're also very welcome. And this is interdisciplinary group, not only airborne geophysics people. So please contact me if you have a question, interest to join the action group. Yes, tomorrow we have the 2.5-hour session in the evening in Europe. To present more details of the outcome of the workshop and discuss more details. Not everyone for interest can join the workshop in June, so we would like to collect more comprehensive input from the community. Thank you very much.
Thanks very much, Kenny. That was the full 15 minutes, but since we are ahead of time.
Yeah, we have time for questions. So since Kenny has asked many questions to himself, it's like now it's the audience that can ask questions starting with, "Hey, Kenny."
Please.
So are there any questions? If you wish, you can also raise your hand and I can unmute people as well if you don't want to type.
Or I can see many people who attended the workshop. So if I miss some important point, please follow it up.
Oh yes, and there are the RINGS stickers.
Yeah, Ralph has his hand up.
Okay.
Yes. Hello, Kenny and everybody. I have a bit of a logistics type of question. So this is a great project, but it also seems to be a gigantic enterprise. How realistic is it to achieve these goals in 4 years?
Okay, yes. First, we do not plan to send a single airplane all around Antarctica. It is not possible. Rather, we would like to combine the project in the different regions together. And then we don't know, we can finish up all the measurement in 4 years. So, but we wanted to extend the action group only for 4 years, because if we say 8 years, we do not really have milestones for all 8 years. So we want to see, we want to act first in the first 4 years and want to review the achievement and think again. That's a plan. And then yes, we're really concerned. We think that we really need to work hard to get the result out soon, because you see that the funding cycle already takes, say, 2 years until the field work, and then a lot of projects are pending. Well, a lot of projects are funded already, but were not conducted in the field because of Corona. So we don't know how much we can really achieve in the 4 years, but we already have at least one pending project to make the links. So we would like to finalize the protocols of the common survey in this year so that we can start the measurement very soon.
Okay, thanks.
Thank you.
Any other questions? Okay, well, Kenny, thank you very much for this presentation, and
Thank you.
yeah, I will try to be present on the next session that you organize on rings. So our next talk, and I'm very happy to announce it, because we have a session that is bipolar, and even though it is SCAR Antarctic research, but we have a presentation on Greenland, and so I'm very happy to announce here Michele Petrini on melt elevation feedback in Western Greenland. So Michele, you can share your screen and go ahead.
Yeah, thank you for the introduction. Can you see now my screen?
Yeah, but it's just a small thingy. Yeah, now we see it completely.
Okay, perfect. Thank you. So yeah, I'm gonna present here some work that I carried out during my postdoc at TU Delft. So in collaboration with Miran Witzkaino research group at TU, and also Bill Lipscomb and Gunther Legai from NCAR. And so just to give a quick introduction, we investigate the long-term evolution and stability of the Greenland ice sheet. This is modeling and using a CISM ice sheet model. And in particular, we actually look for thresholds in SMB or global mean temperature for ice sheet retreat. We try to identify the sectors of the ice sheet that are more vulnerable to SMB change and the associated timescales for ice sheet retreat. There is some nice literature that asked already this question. So for instance, for the global mean temperature thresholds, there is somehow a certain degree of agreement on the temperature thresholds themselves. Robinson et al. And Leverman et al. Between 0.8 and, well, in one case 2.2, another case 3.2 Kelvin warming, and for ice loss, and also in Gregory et al. To 20 more, the more recent study, the ice sheet is mostly lost above 3 Kelvin warming. But there is a disagreement on the existence of threshold behavior or not. There are Robinson et al. 2012 found intermediate equilibrium states, whereas Leverman et al. Found an abrupt transition between a stable configuration of the ice sheet and ice-free. And in the last study by Gregory et al., there was a wide range of equilibrium states, so three quite different answers to this question. And there are also other studies, and Pattyn et al. 2018 found that the northwestern sector is more sensitive to SMB changes due to relatively low accumulation and ice flow. And in this study, the northwestern sector, I don't know if you can see my cursor, is somehow including the central west, northwest, and part of the northern INB basin. And as for the timescales, there are very long timescales between 20 and 10,000 years for low to intermediate warming levels, to quick deglaciation times between 1 and 3,000 years for a global mean temperature warming above 5 Kelvin. And in the last study by Gregory et al., it was found that for an uncoupled run, only 3,000 years were enough to deglaciate the ice sheet, whereas in the coupled settings, more time was needed due to some negative feedback, so 9,000 years. So now to come to the simulation setup, we use a CISM, as I said, and we use a the SMB calculated in the CESM, so Community Earth System model. And in particular, we start from a fully coupled run that was published in 2020 by Montour et al., the 1% CO2 simulation. And from this simulation, we selected multiple time intervals, 23 years long time intervals, which basically correspond to trends in climatology. So we're not talking about a steady state climate forcing. This is a bit of a shortcoming, of course, but that's some nice data that we had that we wanted to test and to use. And we use the annual mean SMB calculated in CESM from each interval to force CESM. And in each run, the SMB corresponding to a time interval is cycled to force CESM until we reach either Greenland ice sheet deglaciation or stabilization. And one thing that I want to clarify, how do we account for SMB changes due to changes in ice sheet geometry? And we use a very nice capability of the CESM that is to run CESM force with the SMB from CESM calculated at multiple elevation classes. So just to quickly explain, in any actually CESM run, but in this particular 1% CO2 run, in the land component of the model, the surface air temperature is downscaled to 10 different elevation classes. You can see the elevation here, and using a fixed lapse rate of 6 Kelvin per kilometer. And then in the land model for each elevation class, the SMB is calculated using a surface energy balance scheme. And then this SMB is saved at each elevation class in annual mean Kappa history files. So in our CESM runs, we actually use these annual mean Kappa history files, which contain information to downscale the SMB forcing at varying elevation to force CESM. And so we are able to account for SMB changes due to changes in surface elevation. Now, I will just go through the results. So first of all, if there is any threshold in SMB for ice sheet retreat. And we actually do find a quite sharp threshold behavior, because for all the runs that we have 3 main final volume states. In this first figure, there is the first group, so more than 80% of the initial ice volume remaining, and this occurs for an SMB forcing that is higher than 317 plus minus 97 gigatons per year, of course, integrated SMB over the Greenland ice sheet. And there is a second final volume state that is around 50% of the initial volume. And this is reached for an SMB forcing integrated again, that is ranging between 255 plus minus 83 and 286 plus minus 24 gigatons per year. And then the third group where less than 10% of the initial volume is remaining. And this is occurring for an SMB forcing that is lower than 230 plus minus 84 gigatons per year. So you can see that this number here, 230, is positive, and this is a quite surprising result, because if we look here, for instance, this is a integrated SMB, SMB anomaly on the top, and final volume. You can see that for these 4 runs that are highlighted in yellow, these runs have a final volume less than 10% of the initial Greenland ice sheet volume, and the initial integrated SMB is positive. You can see the value here. And actually for 3 of these runs, there is not even one single year with negative SMB. So in this case, we have everything due to the melt elevation feedback, and it's a quite strong result. And if we look at the retreat patterns again, we have a different situation. Now I'm gonna refer to the simulation as a global mean temperature increase instead of SMB, just because it's simpler. But what we have is that for a global mean temperature increase lower than 2.8 Kelvin, the only retreat that we have is at the southwestern margin. And you can see here. And for this group of runs, more than 80% of the volume remains. Then for the 50% volume runs, that corresponds to a global mean temperature increase between 3 and 3.2 Kelvin, so quite a narrow band. We have a retreat at the southwestern and also northern margins. And we also have that there are two disconnected ice bodies. So there is the main ice sheet, and then a big ice cap in the south and some smaller ice caps in the north. And you can see that the central western margin, and this is quite important, remains very close to the coast. And there is this topographic height that I will call from now on anchor point, just for make it simpler. And so it remains connected close to the coast. Then for the runs that are losing more than 90% of the volume, there are two different group of forcing. So a global mean temperature between 3.4 and 3.8 Kelvin, of course, a global mean temperature increase. We have that the central margin is detached from the western anchor point, and the ice sheet retreats all the way to the east. And the same happens with global mean temperature increase higher than 4 Kelvin, the very same pattern, but with very much shorter timescales, lower than 12,000 years. And this is also when the initial integrated SMB is fully negative, that the retreat, of course, is much faster. And I want now to have you a look at the behavior of the ice sheet at the central western margin, because it seems to be in our simulation a good predictor for long-term substantial ice loss. So I will start now a video for the plus 3.2 Kelvin run, which is leaving 50% of the volume. And you can see now the video is going to play a bit slow, but the central western margin always remains quite close to the anchor point, even if it's detaching for a little bit, then is connecting again after a re-advance. And this is just a negative feedback because we do have a isostatic rebound, so the elevation increase and so increase the SMB using the multiple elevation classes method. And well, I can play one time more. So this is this video is playing for until year 20,000, but even after that, until 40,000, there is this retreat and this some sort of oscillation due to isostatic uplift and SMB increase. If we now look at the plus 3.4 Kelvin run, so here we are left with 10% of the volume, you can see that the initial phase of the retreat is actually quite similar. So there is a small retreat of the central margin and is followed by a small re-advance. But what is actually changing here is that there is a retreat in the north, and also the central margin is not fully connecting again. So it is now, but after that, after 20,000 years, there is a retreat that is not that the ice sheet doesn't manage to recover from. And so there is a runaway retreat to the east, and this is the final ice sheet configuration plus minus some oscillation. And just to now show you the very last slide, the timescales for a Greenland retreat. For a global mean temperature increase of plus 3.4, we have the higher timescale, 40,000 years, then ranging between 25 and 15,000 years for 3.6, 3.8 Kelvin warming. And then as we increase our global mean temperature warming, the timescale decrease from 12 to 2,000 years. And this 8.5 corresponds to the full 4 times CO2 level in the coupled season run. And just to conclude now, I think that the very important thing to remember for these studies, this sharp threshold behavior ranging between 80%, 50%, or less than 10%, and the fact that for less than 10%, we can we have this very large ice loss starting with an initial integrated SMB that is positive, and also the transition from 50% to less than 10%. There is seems to be a very important role played by the central western margin, and very a large variation in timescales for ice loss. And I just will stop here in case you have questions. I'll be happy to answer. Thank you.
Thank you very much, Michele. Yes, and it was such an interesting talk that there are questions from the audience. And so the first question is from Jill Ramstein again. Do you have any idea of the sensitivity of your results to the fixed lapse rate that you use of 6 degrees per kilometer?
Yeah, unfortunately we don't, and that's so we wanted, of course, to test this fixed lapse rate, but to do that we need to not use only CISM forced by CLM SMB, but we actually need to run CLM and CISM so that we can change in CLM the lapse rate. And to do that, we need coupler history files from CAM to CLM, but we don't have that, so we would need to run again the fully coupled run. So this is something that requires a lot of computing time to have these files. So we didn't manage to do this, but I think that's it's a high priority to understand this, because 6 is of course just use there is no seasonality and there is no spatial variation. So it could be very important just to verify if actually this behavior is realistic. Yeah.
And then we have another question. What makes the eastern side less vulnerable?
In this case, we have a very, very high accumulation and ice flow at the eastern margin that is simulated by CISM. So in CISM, we have a very strong SMB. So it's more like a wet part of the ice sheet. And so when there is a warming, there is not impacting a lot the eastern side, just because the accumulation remains very high, eventually increasing with through some more refreezing or more precipitation. So that's so also if you look at the coupled CISM CISM 4 times CO2 run, or the projection that we have coupled CISM CISM, it is a little bit a bias that we have in the SMB that makes this side very, very strong, very stable also.
Okay, thank you. I had also a question. So this is all governed by the melt elevation feedback to a large extent. What about the albedo feedback?
The albedo feedback is not accounted for here, just because again, to do that we will need to turn on CLM, so that is able to see when the ice returns. So that's another actually very interesting set of simulation to do, because of course we are completely neglecting them. Also, another thing that we are neglecting in the opposite direction. So there is the atmospheric lapse rate and some of the melt elevation feedback, but there is no correction for the precipitation. So we are getting more melt. And if I don't know if you noticed that in the SMB video, there is an increase at the margins for precipitation, but this is only through more refreezing. So we have more melt, some more liquid water is refreezed, and so there is a little bit more accumulation. But I think we are missing a big part due to more humidity and more precipitation.
Okay, thank you. Any other questions, maybe from the panelists? Oh, there is another question that popped up. Okay, that's another question, a remark from someone I was also going to ask about the albedo feedback, surely important as the retreat proceeds. But I think we answered that.
Yeah, one thing that I could maybe quickly add is that there is also now some work. I'm not at 2000 anymore, but Miran Vizcaino and also other member of the research group are now trying to continue some of these low forcing runs fully coupled. So of course I expect that some answer will also come from this new set of simulation.
Okay, thank you very much.
Thank you.
Let's move on to the next speaker, and that is going to be Ralf Greve on future projections for the Antarctic ice sheet until 2300. With Psychopolis, I presume.
With Psychopolis, yes, very right. Just a moment. You can hear me?
Yeah, we can hear you, we can see you. It's just that we are waiting for your screen to be shared.
Oh, sorry.
Yeah, that's important, Ralf.
Yeah, I know. I wasn't aware that I have to do it myself. All right.
Yeah.
Okay, now I should be able to see it.
Yeah, we see the screen, but not yet. Yeah, now it's in presenting mode. Very good. Yeah, go ahead, Rolf.
Yep, okay. Yeah, future projections for the Antarctic ice sheet until the year 2300. And this is in some way similar to the work by Antonio, our first speaker of the session. So let me acknowledge my co-authors first, which are Chris Chambers, Takashi Obase, Fuyuki Saito, Wing-Li Chan, and Ayako Abe-Ochi. Okay, so the background for this work is ISMIP-6, the ice sheet model intercomparison project for CMIP-6. The primary goals of ISMIP-6 were to provide state-of-the-art projections of ice sheet contribution to sea level rise, both for Greenland and Antarctica, and also quantify associated uncertainties, everything intended to be input for the 6th assessment report of the IPCC that was published last year. So in that sense, the main phase of ISMIP-6 is done, as indicated by the number 6, but we are still continuing this work with some follow-up projects, both by individual groups and also by the entire community. So just briefly recap, the ISMIP-6 experimental design basically consists of some initialization plus historical run until the year 2015, which is the starting year for all the actual future climate projections. And until here, it's basically modeler's choice. So you might be spin up, might be data assimilation, whatever. So, but I'm not going to talk about this in detail here because of time. Then the actual projections go in the original ISMIP-6 experiments from 2015 until 2100. And here we had to follow the ISMIP-6 protocol quite closely, meaning that atmospheric and oceanic forcings were given from selected CMIP-5 and CMIP-6 global climate models, GCMs. So this shows the results we obtained with our Psychopolis model for the ISMIP-6 simulations and all climate forces. So it's the sea level contribution in millimeters over time, 1990 until 2100. And you see this pretty large error bar is all the RCP 8.5 or the newer CMIP-6, SSP5 8.5 pathways, while this uncertainty ranges from the RCP 2.6 or SSP1 2.6, which are more kind of substantial emissions of future greenhouse gas emissions. While this one is, of course, a pessimistic scenario, basically business as usual. So what you see here, and again, these are only the Psychopolis results. Of course, these experiments were also done by many other working groups with different models. So you see, first of all, that there's a pretty large spread in the results due to the climate models. Yeah, and it's more or less the same size, the same spread due to different ice sheet models, which I'm not showing here. If you look at the mean values, which is 18.5 millimeters sea level contribution for RCP 8.5 and 8.4 millimeters for RCP 2.6, it's not nothing, but it's not the big disaster either. So I would call this a relatively limited mass loss. However, evidently the range is quite large, and we can, at the upper end of the range, we can get a pretty significant mass loss of, at least for Psychopolis, like 10 centimeters and more. Some other models had even more, if I remember well. But on the other end of the range is also the possibility for a slight mass loss. So a negative contribution to sea level rise, which is because of generally increasing precipitation over the Antarctic continent that counteracts the mass loss due to sub-ice shelf melting. Okay, so what we did in this study is we extended the simulations until the year 2300 with Psychopolis, and we also extended the climate projections until 2300. So it's not just a repeated climate, something like a repeated late 21st century climate. However, we rather extrapolated the climate forcings into the future. And this we did by a method called climate indices. So again, the problem is that you do not have the GCM simulations until 2300. Yes, there are a few selected results, but not many. So what we did here instead is we used a single simulation from the MIROC 4M GCM until the year 2300 and used the results to construct a bunch of climate indices. So what you see here is these are 4 different climate indices for the atmosphere: surface temperature, precipitation, evaporation, and runoff, and a single climate index for the oceanic forcing, which is the mean ocean temperature at some intermediate depth around Antarctica. And the idea is that we just lump the entire MIROC 4M results into a single number for these parameters, such that the 1995 to 2040 means, which we might call the present, are mapped to the number 0, and the late 21st century values are mapped to the number 1. And note that this is always the case, no matter whether we have RCP 8.5 or 2.6. So this actually means different things for the different climate scenarios. Okay, and then you see these different indices here. Red is RCP 8.5 and blue is 2.6. And you can see clearly that in all cases for the 8.5 pathway, the climate forcing gets stronger beyond the 21st century. So 1 is late 21st century, but you see for the surface temperature, we reach something about 3, precipitation, even a bit more, evaporation, a bit less. Runoff is very high, up to 10, but runoff is not so large in absolute terms. So that actually doesn't contribute that much, because present day runoff is relatively low. And the oceanic forcing is a bit more inert. So for the atmospheric values, you always see some kind of saturation in the late 21st century, which does not really happen for the ocean, which goes on into the future. It would probably increase even more if you continued. For RCP 2.6, we see that for most atmospheric cases, it actually the climate forcing actually falls back below late 21st century forcings, meaning that we get values something between 0 and 1. It's different for the atmosphere, which is again a matter of inertia. So here for the atmosphere, we end up with values which average approximately around 1.5 in the more distant future. So this even produces more climate forcing. So as I said, I don't have time to explain the method in detail, but the idea is then basically to use these indices and combine them with the ISMIP6 forcings until 2100, to construct extrapolated ISMIP6 forcings until the year 2300, each for these different parameters here. Okay, let's have a look at some results now. Well, this is basically a similar plot as we've seen before for the standard ISMIP6 experiments, sea level contribution, time until 2300 now. So first of all, if we look at the constant climate control run, it's this black line here, and we see that the ice sheet is actually very stable in this unforced scenario. The time until 2100 is identical to the original ISMIP6. It just looks different now because we have a different scale. So please note, now we're talking about meters, not tens of millimeters anymore. So it's pretty substantial. So this is ISMIP6. If we look beyond that, we see clearly that really not only quantitatively, but also qualitatively, a different picture emerges. So one thing is that now clearly the RCP 8.5 and RCP 2.6 scenarios kind of branch out. So we get clearly different responses. There is a bit of an overlap such that there's one pretty insensitive RCP 8.5 scenario that's within the 2.6 range, and this one is only a little bit more, but most of the RCP 8.5 experiments produce a meter of sea level equivalent or more by 2300. So this is really a different story now. While RCP 2.6, it's only 3 simulations actually, but in all these 3 simulations produce a relatively limited contribution. So the average is about like 16 centimeters compared to an average of 1.5 meters for RCP 8.5. The most extreme case is something like 3.3 meters here. So this is really a different thing now compared to just looking at the 21st century. As Antonio already mentioned, most of the big contribution comes from Western Arctica, and it's related to a developing marine ice sheet instability in the area. So which means we're really crossing a tipping point in the system here. We did an earlier intermediate study where we did a different approach further into the future. But in that previous study, Chambers and others, 2021, we assumed for the beyond the 21st century, actually a sustained late 21st century climate. It was just repeated beyond 2100. If we compare this to our new extrapolated forcings, we see that now we get about 2 times more. Yeah, so this is the same statistics for these previous simulations with just a repeated late 21st century climate. If you just have a quick look at the averages, you see here for RCP 8.5, it's 1.5 compared to 0.8 meters. For RCP 2.6, it's about 16 centimeters compared to 6 centimeters. So very roughly, it's a factor 2 more as a consequence of really ongoing climate forcing beyond the 21st century compared to rather keeping the 21st century stable. Okay, a quick look at the regional mass loss. That's again the entire ensemble of simulations. So this is 8.5 versus 2.6. Sea level contribution, the scale is by a factor 10 different. So please, this is much less in reality. And as I said before, we can clearly see that for the stronger forcing, most comes from West Antarctica. Yeah, East Antarctica, it depends. In some scenarios, it can be up to a meter, but it's basically less. And again, some produce even a negative contribution, which is this precipitation feedback I already mentioned. Yeah, increased precipitation that can be dominant over East Antarctica. For RCP 2.6, however, kind of East and West Antarctica approximately comparable, a bit more for East Antarctica, but again, we are generally much lower, so it's not that much. And Antarctic Peninsula is more or less 0 plus minus. Yeah, but for RCP 8.5, it can also contribute somewhat significantly compared to the relatively small amount of ice we have. But again, in both directions, can be positive or negative. Okay, now towards the end, I would like to have a look at one scenario as an example, which is the MyROC ESM Chem RCP 8.5 forcing. So this plot here shows the components of the global mass balance. Which is first of all the volume change. That's the green curve here. Yeah, so we see again until 2100, okay, somewhat, but then it kind of speeds up, yeah, because of this West Antarctic ice sheet instability. Surface mass balance remains positive. It gets more oscillations. On average, it goes down somewhat, but it's like 3 times 10 to the 12 cubic meters per year, and here it averages about 2. There are other scenarios where it actually does get negative. Yeah, so but not the case for this particular scenario. And then evidently the basal mass balance, the blue curve here, is evidently dominating the entire mass balance. Yeah, so which is mainly, in the first place, mainly sub-ice shelf melting, but then because of the reduced buttressing, it also leads to a decay of the grounded ice sheet. Carving is also somewhat significant, but it doesn't change that much over time, with the exception of that phase here, which is a pretty strong collapse of the Ross ice shelf, as we will see in a moment in some videos. And by the way, so this is a slightly more than average scenario, which produces about 2 meters of sea level equivalent ice sheet decay by 2300, and most is from West Antarctica, 1.7 meters. Okay, 2 videos towards the end. It's again MyROC ESM Chem RCP 8.5, and that's the ice thickness. Let's get this started. It's not the thickness change, it's just the thickness. So in the 21st century, not that much.
We're at about 14 minutes now.
Okay, I'm almost done. So now here, this is this Ross ice shelf collapse I mentioned. Yeah. Okay, here you see also in the Pine Island Thwaites area, pretty strong decay. Let's have a look at the surface velocity at the same time. Okay, again, in the 21st century, not that much is happening. Now look here, Pine Island Thwaites and also Ross ice shelf. We saw similar behavior in the first talk by Antonio. I think he also had a pretty strong response in these 2 areas. So Ross Filchen-Rönner remains, but also changes quite a bit. Amery disappears, but there's not that much feedback on this Lambert Glacier system further inland. So most of the response is West Antarctica. Okay, I'm at the end. So we have seen that there's a pretty severe mass loss plus West Antarctic ice sheet instability under RCP 8.5, much more limited under RCP 2.6, which is more or less in line with the Paris Agreement, meaning that if you want to keep the Antarctic ice sheet under control, climate change mitigation is really crucial. And let me point out, I mentioned it before, there is now a community initiative, ISMASS 6 projections 2300 Antarctica, which will have more climate scenarios, other ice sheet models, and also probably look a bit more into feedbacks of changing ice sheet on the forcing. And that's all I have to say. Thanks a lot. And I'm looking forward to any questions, of course.
Thank you very much, Rolf.
Sorry,
yeah,
Frank,
go ahead, Rupert. Go ahead.
I was just going to mention we've caught up with ourselves now. We're back on schedule, having had a fairly relaxed few presentations.
Right, are there any questions from the audience? I don't see anything in the Q&A. I do have a question, Rolf, for this very interesting presentation. You're talking about tipping points of the West Antarctic ice sheet, the tipping point reached. But did you check how the accumulated amount of melt relates to the mass loss of the West Antarctic ice sheet, and whether that is deviating from it, meaning that, yeah, normally if you have a tipping point, it means that your grounding line or your mass loss should continue irrespective of the forcing.
Okay, well, I can show you something from the study from Chambers et al. This, as I mentioned, so this went until the year 3000, but with a late 21st century climate. And in that case, we always got something like moderate decay, quick decay, and then leveling out. Yeah, so now we're at 2300, but we haven't tested in detail, but I'm quite sure if we continue these types of simulations that we did here into the future, it would look something similar. Yeah, it's just that in our news until 2300, the stuff is just going on. Yeah, well, here you can see how it then really, it kind of at some point when almost everything is gone, it levels out again.
Yeah. So in your new simulations, this accelerated part comes earlier in time now.
Yeah.
And is this only due to the climate forcing that you used, or are there other reasons behind this?
No, it's the climate forcing, because again, now we are really continuing the stuff into the future. So it gets ever stronger. While in these other simulations I just showed, we just keep it at late 21st century conditions.
Okay, thank you very much. Any other questions? Yes, Ankit asks, there is less impact on grounded ice upstream of Amory than other West Antarctic ice shelves. What do you think is the reason behind this? Is it due to the difference in subglacial hydrology or something else?
Yeah, I think it's mainly just the topography. Yeah, it doesn't have these pronounced marine ice sheet regions where the base is really below sea level at extended regions, which allows this instability to happen so strongly.
Okay. Thank you.
It's not nothing, by the way. I mean, it does lead to some buttressing loss, but again, compared to what's going on in Western Antarctica, you don't see so much. You would have to zoom in a bit closer to really see the effect.
Yeah, the Amory is a really narrow zone. Yeah. Okay, if there are no further questions, and since Rupert, the watchdog, says that we caught up in time, then we can move up to the next presentation, which will be given by Diana Segala on Antarctic ice sheet simulations, again with the Yelmo ice sheet model.
Yeah, hi.
Hi, if you can put it in presentation mode.
Yeah, it's not. Oh, wait, I have to.
Yeah, it's probably depending on what's you're using multiple screens or something.
Yeah.
Yeah,
Sorry.
yeah, that's always a
I'm-
problem.
I'm sorry. I'm going to change that.
Yeah,
Okay.
by the way, there is still another question while Diana is trying to set up. It's a comment from Roland. There is some retreat in Totten and Moscow University region. I don't know whether Rolf wants to comment on that.
So I will. I'm sorry. I thought it was okay, but
Sorry, I was muted. Okay, well, no special comment about it, but just very generally speaking, of course, there is already a bit going on in East Antarctica. It's again, it kind of West Antarctica kind of dwarfs it. But of course, if you look closer, you can find a couple of interesting features also going on in East Antarctica. And again, the simulation I showed you was a one that has an even relatively strong response in West and less in East. There are others that have more response in East Antarctica. So it's worth a closer look. Thanks.
Okay, Diana, do you manage to get your
yeah, I don't know if it's going to, yeah, maybe
Yeah, it's not presenting mode, but okay.
Hello, but normally
It's large enough for me, but then again, I have this huge screen in front of me.
Yeah, but it's too bad because I have a PDF.
Okay, that's maybe
presentation, but
easier.
yeah, but it's I just find out that it's not the codes.
Okay.
Yeah, it's really a mess. I'm sorry. So yeah, I can try, but it's too small. I think it's not cool for you. Yeah, it's the first time. I'm sorry. Normally, it's always well. Is it okay if I'm presenting?
Yeah, you can present it.
Like that.
It was rather big.
Sorry, I think.
Yeah,
It's okay.
right.
You see the slide. I'm sorry.
We can
Well,
see it.
okay.
It's visual. Good.
Sorry,
Well,
sorry.
go ahead, Diana.
Yeah, sorry. So thank you. Good afternoon, everybody. So I'm Diane Segala, and I'm a second year PhD student at the LSE, the Laboratory of Science in Climate and Environment. I'm working with Gilles Ramstein and Florence Coloni, and also a work group in Madrid. And the subject of the work I'm presenting today, it's the Antarctic ice sheet simulations with YELMO, the ice sheet model, and also some climate simulations with IPS LCM5A2 for the mid-Miocene period. So first, some words about the mid-Miocene period. So we have the MMCO here from 16.9 million years to 14.7 million years. And the MMCT, it's the mid-Miocene climatic transition from 14.7 million years to 13.8 million years. And at the end of this period, we have a colder step, which is the MMG, the mid-Miocene glaciation. And globally, the climate was warmer than today, and it's mostly due to changes in orbital parameters and also PCO2. And then we have also just only one ice sheet, which is Antarctica, and it's a good configuration to study the sea level changes because, as you can see, when the climate is colder, we have an expansion of Antarctica and the sea level drop. And concerning the PCO2 concentrations, it was between 400 to 800 ppm in average, but we have a lot of uncertainties and mostly at the MMCO. So we took two values for our experiments, and you will see afterwards it's 420 ppm and 700 ppm. So the problematic, here is the questions we want to answer. So how does the Antarctic ice sheet behave at the MMCO and the MMG with the climate simulations? How does it react with the PCO2, higher PCO2 than today? And also with the sensitivity experiments, how does it respond to changes in astronomical forcings? So first, I'm sorry. Okay, the methodology for our models. First, the climate model, which is IPS-LCM5A2. So we have some steady state snapshots at the Miocene and some sensitivity tests with the PCO2 and orbital parameters forcings. And then we are using those climate outputs to force the ice sheet model YELMO, like the temperature, the precipitation, or the surface elevation. And then like that, we can perform some simulations to study different Antarctic ice sheet envelopes with, for example, the ice thickness, the ice volume, or the surface mass balance. Then it's just a little summary of the main boundary conditions we used. So for the experiments, we have two references simulations. It's the MMCO 700 and MMG 420 ppm. And we have 7 sensitivity simulations. It's to study the PCO2, the paleotopography, and the insolation impacts. For all our simulations, we used the topography from Frigola et al. In 2018. And for the bathymetry, it's from Müller et al. In 2008. But we put some changes, and in particular in seaways, because for both periods, it's really different. Like the Tethys, it was closed at the MMG and open at the MMCO. And for Arabia, we have, for example, an embayment at the MMG and a shallow seaway for MMCO. We changed also the depth of the Greenland-Scotland ridge and also more changes. Then concerning the ice sheet, we have for the MMG, we prescribed in average, well, 80% of the Antarctic ice sheet of today and 50% for the MMCO. Concerning the orbital parameters, for the reference simulations, it's from present day. And for the sensitivity, we have the minimum and the maximum insolation at 75 degrees south in summer. And finally, for the vegetation, it's coming from PLIOMIP2 in Conto et al. In 2012. So for the sensitivity experiments, we are exploring that because it's playing a big role at the Miocene, mostly with the paleogeographies, the PCO2, and the variations in insolation. So here are the topography we prescribed in the model. So it's for the control pre-industrial, it's for today. Then the MMG, it's quite similar as today. And finally, the MMCO, it's really smaller, and it's it's globally 50% of the Antarctic ice sheet of today. Concerning the PCO2, so we have a lot of uncertainties, like I said, for this period, and some studies say that we can have more than 800 ppm, but we have here for our simulations 420 ppm and 700 ppm. And finally, for the insolation, so we computed the maximum and the minimum insolation with Lascar et al. In 2004, with the obliquity, precision, and the eccentricity. So concerning the results, here it's the outputs of YELMO, and first for the MMCO 700 ppm. So at the top row, you have the surface elevation, and at the first step and the final step in YELMO, so after 30,000 years. And at the bottom row, you have the anomalies in insolation. So it's always maximum minus minimum insolation. And we have the mean annual temperature and the ice thickness. We wanted to analyze that because like that, we can see if we are far or not with the reference and what we prescribed at the beginning. And also, for the surface elevation, it's to know how is the evolution is in YELMO. And here for this simulation, we can see that it's similar at the beginning and at the end. We have quite the same topography, just maybe here we have more ice, but it's maybe more interesting to check the anomalies, insolation anomalies, because we can see that it's warmer here on East Antarctica, and we are losing some ice sheets then as a feedback, there is an ablation, but it's just a few impacts of difference in insolation, because if we have a look at the other simulation for MMCO, but with 420 ppm, it's even more. Actually, in the YELMO, in the simulation, at the end, we are gaining a lot of ice sheet. It's there is more ice sheet at the end, and it's even more warm. And also we have losing a lot of ice thickness here on the south of East Antarctica. So we have a huge impact of the insolation for this simulation. And finally, for the MMG, it's that 420 ppm. So here it doesn't change a lot. We have quite the same topography for the surface elevation, for the first time step and the final time step in YELMO. And also in anomalies, it's not really significant. We don't have a huge impact of insolation for the MMG with 420 ppm. So we can conclude first that at the MMG, we have an Antarctic ice sheet in equilibrium in YELMO. The topography is quite similar in the initial conditions and at the end of the run. So the Antarctic ice sheet response to insolation anomaly is really weak. So we have a stability of the Antarctic ice sheet. And we can say that it's consistent with the climates that we prescribed. But for the MMCO, we have an Antarctic ice sheet which is not in equilibrium in YELMO, because for 420 ppm, the effect is really notable. And also a little bit for 700 ppm. So maybe it's because we will have more PCO2 than 420 ppm or 700 ppm, or it's related also to the ice sheet, because we can prescribe a big ice sheet. Maybe it's smaller than we thought, or also there is an effect of other greenhouse gases. So we have to work again on these simulations and to maybe to change the boundary conditions and to explore the different forcings. And we can see also this conclusion with the ice volume. So this is the ice volume for all the simulations and also some studies. Actually, we don't have the same boundary conditions and the same models, but it's just to have a look, to have an indicative comparison, because it's always good to know if we are in the range or not. And actually, Frigola et al, they took some really realistic boundary conditions, and Gasson et al, it was more idealized, but it's really interesting because we can, with all the studies, quantify the effect of the PCO2 and the insolation. Because if we are doing the difference between the MMCO 700 ppm minus MMCO 420 ppm, we have a difference in ice volume of 10 million cubic kilometers. And if we are just looking at the insolation effect with the MMCO 700 ppm minus, maximum minus minimum, it's minus 7 million cubic kilometers. And for the MMCO 420 ppm, it's minus 13. So it's the most sensitive case we have. And there is a huge impact of the insolation at MMCO with 420 ppm. So it's just the perspectives we will work on. And that's it for me. Thank you.
Thank you very much, Diane. Are there any questions? I don't see any questions in the Q&A. Unfortunately, we are also a bit now running behind time for the first time instead of ahead of time. If there are no questions, then thanks again, Diane, for this very nice presentation. And we will move on to the next speaker, the next to last speaker. It's Chen Berends on compensating errors in inversions of subglacial bed roughness. Chen, you can share your presentation. That should work.
Get the message that I need to allow this in my system preferences first, of course. There we are. Can you see this, Frank?
Yeah, but not in presenting mode. And now it is. So that's
Great.
perfect. You have the floor.
Right. Thank you very much. Good afternoon, everyone, or good some other part of the day if you're not in European time zone. I'd like to tell you a little bit about some schematic experiments I've been doing regarding basal inversions, which is a nifty little mathematical trick to help an ice sheet model become a little bit more accurate. Just really quickly recapping what this is. An inversion is basically answering a backwards question. Usually when you have an ice sheet model or a climate model or whatever, usually what you do is you solve what we call a forward problem. So you input a set of causes and you calculate an effect. So you have an ice sheet model, you tell it how the climate is changing, what the continent looks like, etc. And you determine how the ice sheet will evolve as a consequence of those causes. That's what you call solving the forward problem. An inverse problem is taking it the other way around, saying, okay, we know what the ice sheet looks like, and we want to know what one of those inputs look like, because we don't know it perfectly. And very often this is done either for the roughness of the rock underneath the ice and/or for the viscosity of the ice, because those two are very difficult to constrain directly from observations. And there you have the inverse problem, which I have on the slide in the italics here, formulated as what should the roughness of the bed underneath the ice be in order to produce the ice sheet that we're seeing today. That's the inverse problem. That's what you often want to solve. And typically people do this with either one of two different sort of mathematical families of tools, where the one is this iterative procedure where you run an ice sheet model forward in time and you sort of nudge the roughness field until you achieve an ice sheet that looks like the observations, or like what you call the target. And the other family is what you would call a data assimilation, where you don't actually run the model through time and you try to match the velocity field to observations and or the thinning rates, which is based on a slightly different set of assumptions, but fundamentally it's still answering sort of the same kind of question, trying to use observations on the shape of the ice sheets to say something about the roughness of the bedrock underneath it. That's what basal inversion is. Now, that all sounds simple enough when you put it like that. However, this is what the kind of results that you get when you do this. These are figures I shamelessly copied from publications from Mr. Frank himself and from Dave Pollard from a couple of years back, where they did this for Antarctica to try and get a grip on, okay, how rough is the bedrock underneath the Antarctic ice sheet? And you get these nice psychedelic looking pictures of the roughness field. Now, that all sounds very nice. However, this method is intrinsically based on a couple of assumptions, because the forward problem, as I just summarized it, is you make assumptions about the bed roughness, about the topography, about the climate, about the ocean, about all kinds of stuff in order to calculate how the ice sheet evolves. If you do the inverse problem, calculate the bed roughness, you still make the same assumptions about all the other components of the ice sheet system. So about the climate, about the subglacial topography, etc. And basically in your inversion, you solve for the bed roughness based on assumption of those other quantities. And what I wanted to know is what happens when you make an error in one of those assumptions. So just to give you an example of what I mean there, say I do this with my ice sheet model and I tell my model a certain value for the ice viscosity, which is wrong. Say I overestimate the viscosity in my model. That means that in my model, the viscous flow of the ice will be slower than it should be in reality, which means that in my model, my ice will grow too thick. Now, if I run this inversion, and I do this with this nudging approach, my inversion will try to compensate for this, saying, my ice is not flowing fast enough. That probably means I'm overestimating the roughness of the bedrock. And I will try and decrease that to match the observations. So my model will start to decrease the roughness underneath the ice too far in order to compensate for the lack of viscous flow. And it tries to compensate for that by increasing the sliding. And if you do that and you're not too far off with your estimation of the viscosity, then this inversion procedure should probably be able to give you the correct geometry based on the wrong values of viscosity and roughness. And what I wanted to know is, how big are these what you call compensating errors? Because that is fundamentally what they are. What do they look like? And especially if I have a model with these compensating errors built into it, how does it behave when I study the future evolution of an ice sheet, which is basically what a lot of us are paid to do. Now, initially, I thought I'd just apply all this to the Antarctic ice sheet, but it's very difficult. I don't like doing that, so I took a step back and went to look at what you'd call idealized experiments with a very, very simple geometry, which makes my life a lot easier, because in that idealized setup, you know everything. You know what the climate looks like, you know what the topography looks like, you know what the viscosity looks like, because you made all of them up. That's the big advantage of having an idealized experiment. So that's what I did. And this is what it looks like. It's almost identical to the MISMIP plus geometry experiment, which I think most of you will be familiar with. It's an idealized one. It sort of describes this glacial valley with an ice stream running down it. And at some point it reaches the ocean and it becomes afloat, and it feeds into this small shelf. Right? It's about 800 kilometers long downstream. It's about 80 kilometers wide. So it's a big valley with ice flowing down it. Most of the stuff like the surface mass balance and the ice viscosity, they're all uniform, which is very simple, and we like that kind of stuff. The only change I made with respect to the official MISMIP plus one is that I made some changes to the basal roughness, where I introduced the spatial variation, just so that there is actually a pattern in the bed roughness that I should want to reproduce with my inversion, so that I can see whether or not the inversion actually works. And that's immediately what I'll start with the first set of results. And that's just to show you what comes out of my inversion routine when I apply it to this geometry with no errors in any of the other model components. So what you'd call an unperturbed inversion, where I know everything perfectly. And then what you see in the left column are, from top to bottom, are in this case, the tilt friction angle. So that's a measure for the roughness of the bedrock. You see the surface elevation, which looks a little bit like the pride flag, but that's just the surface elevation running west to east. You see the surface of the ice going down, and you see the resulting velocity field. That's sort of my perfect solution. That is, in a way, this is my sort of synthesized observations. This is what the ice sheet looks like. And then on the right, you see the differences with respect to these observations that come out of my model when I run my inversion. So I let my model determine what should the bed roughness be in order to reproduce this observed geometry and velocity. I've run this at 2 different resolutions just for fun. And in both cases, you see errors in all 3. So both in terms of the reproduced ice sheet state, the geometry and velocity, and also in the reproduced bed roughness that are negligibly small. So the inversion itself works. If you know everything else perfectly, then mathematically it is possible to reconstruct what the bed roughness is, even if you don't know it directly. Which is nice. I mean, of course, this is known already, but I wanted to check it for myself. That's cool. Now, what I did is I ran the exact same inversion model again, but I introduced some errors to some other components of the model. So, for example, to the ice viscosity, which, as I said before, this is the flow factor, to be precise, is a uniform number, and I just increased that factor by, I think I did 25%. So medium-sized error there. I introduced errors to the mass balance, both surface mass balance and the melt rates. I introduced some errors to the subglacial topography, which in reality we also do not know perfectly, as Kenny also described in detail in a previous presentation. I introduced some errors to some parameters in my sliding law, all kinds of stuff that in reality you don't know perfectly, and therefore it is conceivable that if you have a model of Antarctica, you have errors in these model things. And I want to know, okay, how does that affect your inversion? What you get is this, and this is a lot of information, so I'll walk you through it slowly. What you see in every column is a set of experiments where I changed one parameter. So for example, the left one summarizes 2 experiments where I increased or decreased my ice flow factor, my viscosity. That's the high version is increased values and the low version is decreased. And what you see is that in the top row, again, this is the errors in the inverted bed roughness, where you see that, okay, in the in the case where I increase this flow factor, and that's a bit confusing there because increase in the flow factor means a decrease in the viscosity, so the ice flows more easily, and that means that my model has to compensate for that by increasing the roughness to decrease the sliding and to maintain the same geometry. And you see then in the middle and bottom rows that indeed you still get a geometry that's pretty much identical to what you want. You do get a slight error in the velocity, although it's not that big, but you have compensating errors in the viscosity and the bed roughness, which is exactly what I described at the start. Compensating errors, that you still reproduce the ice sheet you want, but based on wrong assumptions. And you see the exact same phenomenon when you make errors in the surface mass balance, in the accumulation rate, in the basal melt rate underneath the floating part, errors in the topography, where this is a bit of a more complicated thing because you still need to, of course, in reality, the surface elevation is known pretty accurately. So it's more like an ice thickness error, actually. And in all of them, you see that most of the time, these errors are, in a literal sense, compensating errors, in that by changing the bed roughness to compensate for the effect of the error, you can still get a steady state geometry that matches what you call the target. So these synthetic observations, that works. It's just that it does so, you need a different bed roughness. So that's just these compensating errors in the bed roughness themselves. And the part that I was really interested in is, okay, they do compensate in terms of the geometry, but what happens when you run the model forward in time and you have to force the ice sheet to retreat? How do these compensating errors affect the dynamic response of your ice sheet? And of course, that's what the MISMIP Plus experiment was made for. Basically, what you do is after everything is spun up and you have this nice steady state, you turn up the basal melt, you let the ice retreat, and you watch what happens. And what happens is this. In the left panel, you just see the ice volume, or volume above flotation, decreasing over time as the ice melts away. It's a 500-year simulation. And on the right, you see the position of the grounding line, which starts for all simulations at nearly exactly the same position, which is, of course, what the inversion procedure tries to reproduce. And you see everything retreat over time. And what you see, especially in terms of ice volume, there is well, nearly a factor of 2 difference between the top and bottom end of my ensemble. So there, the purple lines, I think that's the topography change. The change in the viscosity also has a big effect. So in terms of steady state geometry, there are indeed compensating errors. They do compensate. However, in terms of dynamical response, they do not. And I think that's a very, very nice conclusion of these experiments, that you can, if you translate this to Antarctica, you can have 2 different ice sheet models which make different assumptions about viscosity, topography, sliding, you name it, that are still able to produce the exact same steady state present day Antarctica by way of this inversion. But if you run them forward in time, they will show a completely different retreat rate, because in terms of retreat, these errors do not compensate. That's pretty much summing up my project here. I'd like to thank you very much for listening. And just to very quickly, if you are interested in reading more about this, we have this as a discussion paper in the cryosphere right now. So thanks very much.
Thank you very much, Ten, for this interesting presentation. We have a question from Gilles. Okay, it works for idealized cases, but is it really possible to use such a method applied to the real world? Or in other words, maybe, will it for a real case matter much? That's then my interpretation.
Yeah, because of course, applying such an inversion method, yes, that works. That's a lot of people do this already, and I'm right now applying my own inversion scheme to the Greenland ice sheet, and it works very well. You get a present-day Greenland ice sheet, which looks lovely. I have not yet gotten around to doing the same, basically just this sensitivity analysis for Greenland or Antarctica. I am working on it as we speak. It's still it's in progress. I do expect the difference to be slightly less, just because, and this is sort of an extreme case, I really pushed the errors I introduced to the viscosity and topography and everything. I pushed that to the extremes just to see get the sort of upper and lower bound on the effect there. But yeah, okay, I do expect the same sort of general effect in reality. Yeah, I don't see why it wouldn't be there.
Well, I do have a small question. What is the danger of overfitting? Do you use any regularization?
Yes, there is a regularization term in my inversion procedure. So I think I run this nudging run. It's run forward in time for, I think, 100,000 years. After 50,000 or something, everything is stable, and neither your geometry nor your bed roughness change anymore. Yeah.
Okay. Yeah. Unfortunately, we are running now over time, and so thank you very much, Tyne. So we will now move on to the last talk of this afternoon, and that is Fausto Ferraccioli. Is that correct, the way I pronounce it? I
yes,
just stick to Fausto. That's much easier. And this is on 4D Antarctica. If you can share your screen, that would be lovely.
Okay, so hopefully, can you see?
Yeah, but yeah, now we are in presenting mode. Perfect. I give you the floor. You can start immediately.
Thank you very much. So I'm just going to give you a bit of an overview of a project we're currently working on, which is funded by the European Space Agency, which is called 4D Antarctica. And the idea within this project is to try and combine aeromagnetic, airborne gravity, and the satellite data to try and link better bedrock topography, subglacial geology, and one of the most unknown basal boundary conditions affecting the Antarctic ice sheet, which is geothermal heat flux. So whilst very large progress has been made over the years in mapping the bedrock topography, as Kenny was describing in an earlier talk, much less progress has been made in actually constraining geothermal heat flux under the ice sheet. And why is this? Well, firstly, because as you can see on the right-hand side, the amount of direct measurements of geothermal heat flux for the Antarctic continent are very few indeed, particularly in the interior of the continent compared to other parts of the world. This means that we have to use geophysical data as a proxy to try and infer geothermal heat flux. In extreme essence, geothermal heat flux is strongly influenced by two components. One is mantle heat flow, and the second one is crustal related heat flow, which is mostly related to heat production within the crust. So recognizing that geothermal heat flow is one of the least understood and constrained basal boundary conditions, An international group was set up within the former CS program and will now continue within INSTANT to try and better put together the solid Earth community and also the ice sheet community in an attempt to remedy to this shortfall in our knowledge of geothermal heat flux. So what we know so far is mostly at continental scale and comes from magnetic estimates that you can see on the top, or from seismological estimates. However, as you can see on the right-hand side, particularly if you compare the results of magnetic and seismological estimates, you can see that beneath the ice sheet we have very large differences in both West and East Antarctica between these two methodologies. So within 4D Antarctica, which is a large-scale effort that is looking predominantly at hydrology, so both subglacial hydrology and superglacial hydrology. There's a small work package that is trying to look at different study areas, 5 in particular, and try and see what is the current state of knowledge of the crust and the lithosphere and subglacial geology and the bedrock to try and help reduce the inherent ambiguities that we have in determining geothermal heat flux. So you can see the 5 study areas here, and you can see those colored circles. Those indicate estimates of crustal thickness that we have from seismology. So these are passive seismic stations. As you can see, still the coverage in Antarctica in the different study areas is still very sparse. So what other products have we been putting together to try and remedy to the paucity in particular of seismological stations? Magnetic data, there are about 3.5 million line kilometers of aeromag data collected over Antarctica, bed machine that you're all familiar with. These are results of inversions from satellite gravity. Here you have crustal thickness and lithosphere thickness. We're working together with René Forsberg on a new compilation of airborne gravity data, and we have ghost satellite gravity data, as well as satellite magnetic data, and in particular, a major update from ESA from swarm satellite mag data. So some years ago, we published the first comprehensive magnetic anomaly map for Antarctica. As you can see, there are still significant gaps here. And one effort that we've been involved in together with our German colleagues has been trying to conform the high frequency content of the aeromag data to the long wavelength component of the satellite mag. And we've been doing this not just for Antarctica, but also for other continents that were formerly adjacent within Gondwana. And you might ask, well, why is this relevant to geothermal heat flux? Well, it's actually of crucial importance because we know much more about the geology of formerly adjacent continents. So by using magnetic data, we hope to be able to extrapolate some of that knowledge also to the known in Antarctica. And this is a scheme that shows you one of these attempts to extrapolate geothermal heat flux from Australia, India, and Africa into Antarctica. So far, the results have been mostly in the Amundsen Sea embayment, where we have used magnetic anomaly data to try and infer geothermal heat flux. And this is done by basically looking at the bottom of the magnetic sources. Effectively, rocks lose their magnetization at the so-called Curie isotherm, which is also variable depending on the rock composition, but generally is taken to be at about 580 degrees C. So using that proxy, we discovered that quite remarkably, actually, under Thwaites Glacier, there's an area of high geothermal heat flux, which is not directly beneath the so-called linear rift structures that underlie the West Antarctic rift system, but actually seems to be focusing mostly on the flank of the rift, quite close to the outcropping volcanoes. Equally, we found, using magnetic data, an area of high geothermal heat flux along the coast. And this is a very interesting result because independent estimates derived from GPS measurements suggest very high rates of viscoelastic uplift along the coast that might indeed be related to a low viscosity hot upper mantle beneath this region. So I think this is quite an interesting result in terms of geothermal heat flux for Thwaites, and I encourage the modeling community to start using this new product to try and test what effect this might have on this crucial part of the ice sheet. Another area where we have collected new data is at South Pole. This was an area which was largely devoid of data because even satellites can't collect any data due to the inclination of the orbit. And here we have new magnetic and gravity maps. And most surprisingly, we found that although the margin of cold East Antarctica goes pretty straight in the hinterland of the Transantarctic Mountains for over 2,000 kilometers, at South Pole it seems to have a remarkable jog. And so the boundary of the craton is several hundred kilometers further inland than previously known. This is very important as a potential new boundary condition to look at geothermal heat flux under the lake districts at South Pole and beneath the Pensacola embayment. Another result from modeling of the lithosphere comes from Bayesian inversion of satellite gravity data. And here we found that we can test, let's say, hypotheses for crustal thickness and sediment infill in sedimentary basins, at least at large scale, also using satellite gravity data. However, I should say that, like in any inversion, of course, the starting model is particularly important, and I will come back to this in other slides. Other work that has been going on, you saw there was quite a complete aeromag map in 2018, but the magnetic community has been extraordinarily active since then in trying to collect more data, and this was presented for the first time at SCAR. Some 700,000 line kilometers of new data have been collected, and we started to analyze this and merge it with the satellite mag data to try and see if we could improve upon existing products of geothermal heat flux from magnetic data. And so this is a sneak preview of our preliminary results. I've only seen them myself this morning, so they're really, really new. So on the left-hand side, you have the Martos et al. Product that was published in GRL. And you can see perhaps one of the most enigmatic features here was an area of shallow Curie depths and hence high geothermal heat flux in the Saipol coast region, which had very little resemblance with the rather thick crust in the area and relatively thicker lithosphere in this segment of the West Antarctic rift system. However, with our new satellite-conformed magnetic data, we have a much more complex pattern in West Antarctica, and we don't see anymore this very large blob in the single blob in the Saipol coast region. Instead, we see much more detail, particularly in the Thwaites glacier region. The picture is also quite different in East Antarctica. For example, under the Gambertsis subglacial mountains, we seem to have some regions of elevated, shallower, Curie depth, which could be indicative of higher geothermal heat flux than expected. Now, this is all very well, but to actually progress our knowledge of the shorter wavelength, we need to really start doing modeling, and we've started to look at this particularly in the Wilson Glacial Basin. The reason for this being dual. One is that there are many subglacial lakes in the region, and secondly, there's quite good knowledge of the geology along the coast because we can correlate the geology with Australia there. So without going into too many details, I'd just like to show you a snapshot here. This is the new magnetic anomaly compilation for the region, and I'll draw your attention to the colors. So this purple linear feature that you see maps for the first time some of the oldest rocks in Antarctica, Archean rocks. And these rocks are typically very cold rocks, rocks which typically, let's say, feature within the crust quite a low geothermal heat flux. You can see there's a remarkable contrast with these whitish colors here, which instead map for the first time the extent of younger granitoids. These are about 1.6 billion years old that can now be traced several hundred kilometers under the catchment of Mertz Glacier. And this is also readily apparent when you look at satellite magnetic data. So this is a really nice proxy for looking at the extent of these heat-producing rocks under the ice sheet. And you can now compare some of the results of the Martos and our rendering of geothermal heat flux. And you can see that whilst the overall patterns are maintained, we do see relatively lower geothermal heat flux values that, in my opinion, are more realistic geologically. However, of course, we still have to add the complexities within the crust of heat-producing elements. Nevertheless, this is a starting point. I won't go into detail into this, but effectively, how can we progress from this? Well, we can look at the geology outcropping along the coast and try and use the information that we have also in Australia to extrapolate this under the ice. So this would be a next crucial step. However, one thing that I think is a major barrier to looking even deeper into the crust is our paucity of knowledge of a fundamental parameter like crustal thickness. So you can see that if you use the inversion of satellite gravity data under the Wilkes Subglacial Basin, you'll be getting relatively thin crust. Instead, here you have a new product that I combined using existing seismological data, and you can see that these reddish colors of thin crust under the Wilkes Subglacial Basin become purple, so with thick crust. Actually, our new results in terms of estimating geothermal heat flux from the magnetic data would tend to lend more support to the thick crust hypothesis for the region. However, it is clear that we need more seismological stations here to constrain our models. A second part that critically needs to be implemented for next generation models is the distribution of sedimentary basins. So this is from a recent paper of Li et al. That was also presented here at SCAR. And of course, this is particularly important to understand the modulating effects of sedimentary cover on the basement itself and the influence on the hydrology. So this is a big challenge for the community. So I'd like to finish by basically sharing with the ice sheet community the fact that the big successes that the ice sheet community have had in actually pooling their resources to try and come up with a set of models needs to be applied more and more also to the geophysical community, combining the potential field, the seismological and the geological let's say aspects that are related to geothermal heat flux. And basically by mapping bedrock, crust, lithosphere domain, sedimentary basins, constraining better crustal thickness and the structure of the LAB, using boundary conditions such as Curie depth, upper mantle, geothermal heat flux, and intercrustal production, we may be able to get more robust 2D and 3D models of also geothermal heat flux. And of course, this would be a critical step forwards towards understanding the influence of geothermal heat flux on basal melting and subglacial hydrology. And with that, I thank you for your attention.
Thank you very much, Fausto. Are there any questions for Fausto? I don't see anything in the chat right now or in the Q&A. So the product you want to get to is like, can I consider this as like with IMBY for mass balance, is to get like a reconciled product of geothermal heat flow?
This will, of course, be the aspiration. I think probably what can realistically be done would be to test some of this reconciliation in some of the study areas where we have more data. I think at continental scale, definitely in the lifetime of this project, I think it will be impossible. The project is due to finish at the end of November, and we'll probably have an extension but probably not beyond March or so 2023. So, but yes, in the long term, this would be a crucial goal, I think, within INSTANT, to reconcile it pretty much like you guys have very well done in the ice sheet community, I think.
Okay, thank you. Well, if there are no further questions, then this ends our session of this afternoon. I would like to thank, on behalf of my co-conveners, all the speakers that made this a success. And I hope to see you all soon, somewhere. And I wish you a very pleasant afternoon. I also would like to thank the technical office, the IT team, for making this all going very smoothly. And I also would like to thank the audience for attending. And don't forget, there is the e-poster session that you can access through the virtual portal of this Open Science Conference. So thanks again, and have a nice day and final day of the Open Science Conference tomorrow.
Thank you very much.
Goodbye.
Bye.
Thank you. Goodbye.
Okay, thank you, IT team, for this smooth organization. And have a very nice evening.